Hello, everyone. Welcome to class 3 of the ray tracing course. Let me read you this SIGGRAPH ACM policy against harassment. This live stream is moderated by ACM SIGGRAPH. We ask that all comments stay respectful of others and respect ACM's policy against harassment. This means to exercise consideration and respect in your speech and actions, refrain from demeaning, discriminatory, or harassing behavior in speech, and please be mindful of your fellow participants. All right, so let's get started. Can you see my slides? Okay, so let me share my slides with you again. Okay, so this is class 3. So if you are looking for class 3 ray tracing, this is the course to be in. And just to give you an outline of the course, we, in the first 2 classes, covered introduction, how to create a model, sampling of different kinds and multiple samples per pixel. We covered rays and intersections last time, and today we are going to cover scene building and some of the other details. So we have a guest today, Karl, and we'll do some recap. We'll cover some simple shading to convert that into lights, and then textures and multiple objects, and talk a little bit about complexity. So all the stuff today is available in the shader toy. Go to my profile, and all the shaders are public there, and you should be able to see them. And the Google Drive folder has this presentation and the previous ones too. So let's begin by talking with Karl. So Karl is a senior software engineer at Disney Animation Studios. He's working on the Hyperion renderer, and Karl is a member of the team who's obsessed with rendering, as you can tell. If you go to his blog, you'll find out lots of good reading. If you're interested in commercial implementation of a renderer that can trace billions of objects with trillions of rays every day, go look at his blog and learn from him. So let's talk to him live today. Hey, Karl.
Hey, Rajesh. Wow, that's a crazy picture you have of me.
I know, the one I took. So welcome to the course, Karl. And I know a lot of people are interested in hearing from you. And you have done some amazing things with the Hyperion renderer. And you've documented some of them on your blog as well. So I just wanted to talk to you a little bit about your journey to Disney Animation, and then prior to that, your education and how you got interested in rendering.
Yeah, sure, of course. And thanks so much for having me. Yeah, where should we start?
Wherever you want.
Okay, sure. I guess I can give my background. So I've always been interested in, like even in middle school and high school, I was interested in programming. And I think back in high school, I even like downloaded a copy of Blender and tried to use it. And it was, back then, Blender was like really complicated and crazy. And it was before they did a whole bunch of interface rewrites to make it friendlier. And before they introduced cycles to have like a good path tracer and all that kind of stuff. So anyway, so I've always been interested in that kind of stuff. But then when it came time to go to college, for some reason, I didn't think of actually doing computer graphics or computer science or anything related in college. So I applied to business school and got into business school. And on my first day of business school, I realized that I'd made a terrible mistake and business school was not right for me. So I switched to doing computer graphics because just by sheer coincidence, luckily the school that I went to, Penn, had a really good computer graphics program as part of their larger CS department. And yeah, so I originally started thinking that, oh, like doing something more artistic like lighting would be super fun. And I quickly learned that rendering is a really slow process. So this was like 10 years ago at this point. It doesn't feel like it's been wow, it's 10 years ago at this point, a little longer actually, 11. Anyway, so I was trying to use like Mental Ray, and I was trying to use like the Maya scanline renderer and whatever, and they were all kind of like really slow and not super great. And at the time I decided, well, I'm taking computer science classes. I know how to program. How hard could it be to write my own global illumination renderer? I don't know. I'll spend like 6 weeks trying to write a global illumination renderer, and then I'll get back to learning how to do like lighting and fun stuff like that. And 10 years later, here I am still figuring out how to write a global illumination renderer, because it turns out it's a lot harder than 6 weeks to, well, okay, no. As the course and as Pete Shirley's books suggest, you can in fact write your own path tracer in a weekend. And then there's much more you can do in the week after. But then, the third book in the series is titled Ray Tracing for the Rest of Your Life. And I'm squarely in the rest of your life territory now. So yeah, after school, I got a job at Disney Animation working on Hyperion, which is Disney Animation's in-house production path tracer. And I've been here for 6 years, and yeah, it's super fun.
So just to give people an idea about the complexity of a commercial renderer and what kinds of scene that Hyperion is able to render and what the demands of production are, can you just like give a brief overview of like the sizes of the scenes and number of rays we trace and the kinds of images we produce?
Yeah, sure. So a question that a lot of people ask is like, what's the difference between like, what makes a production render like a production renderer? And I've spent a lot of time thinking about that, and I think there's a couple of things, but I think one of the big things is just scale, like the sheer scale of like the scenes and the complexity of the scenes that the render has to be able to efficiently go through. So as an example, a few years ago, Disney Animation actually released publicly one of our scenes from Moana, a full production scene, nothing simplified, nothing scaled back. It's the exact thing that was used to produce a shot in the movie. And that scene, gosh, I don't remember the numbers, but it weighs in at like well over like 100 gigabytes or something in memory, if you just load it completely uncompressed, completely naively, without any kind of optimizations or any kind of out of core systems inside of your render or whatever. And so obviously like the scale of a scene like that, it takes hundreds of billions of rays to produce a single frame. And all of this needs to be done, for every single frame in the entire movie, which adds up to thousands and thousands, hundreds of thousands of frames. I used to remember these numbers off the top of my head, but I don't anymore. But yeah, so the scale of the scenes that we deal with in production typically are in the minimum many dozens of gigabytes, often over 100 gigabytes. And this is kind of that's just kind of the standard, and the artists are always pushing the complexity even further as we get faster computers, as we make improvements to the renderer to be able to handle even larger scenes and even more complicated light transport and that kind of stuff. The artists are always they're always kind of inspired by that, and they're always using that to kind of push their art even further. So yeah, one day we'll have a renderer that can handle terabytes of data efficiently, and at that point the artists will author scenes with terabytes of data because it'll look better and it'll be cooler and it'll make for better movies.
Right. So we also hear about like because ray tracing global illumination is a physical simulation of the light process, but on the artistic side, artists want to do things that are non-physical. Can you give some examples of that? Like what kinds of things that you would have to tweak the renderer to make it work for the artist?
Yeah, absolutely. So yeah, like you said, Rajesh, at the end of the day, we're making movies, not like totally physically accurate light transport simulations, even if what we're starting with is a physical path tracer with physical light transport. So one of the things that the artists are always wanting to push things. Maybe they want stuff to be brighter or darker than it would be in reality. Maybe they want surface reflections or global illumination coming off of like a surface or whatever to be different from what it would be in real life. And that's both to hit what the art directors for the movie are wanting, and it's also to help emphasize like story points. So a great example of that is oftentimes you will want a shadow cast in a character to be darker than it otherwise would be, or maybe you want it to be brighter than it otherwise would be, or you want you want to emphasize like a particular color or something like that. So one of the tools that we have in Hyperion is this thing called a region grad. If any of you are familiar with Renderman, inside of modern like commercial Renderman that you can get off the shelf, there's a tool called I think it's called PXR Light Filter Rod or something like that. So it's the same idea as that. It's basically you can define a region of space, and then within this region of space, you can actually modify your light transport in a otherwise non-physical way. So you can say within this region of space, this is the amount of light that should be bouncing off of surfaces, but I actually want to multiply that by 50%, or maybe I want to bring it down by 20%. And that has the effect of both darkening stuff inside of that region of space, but because it's a global illumination renderer, it spills out into the surrounding global illumination as well. So, things that are being lit by light bouncing off of that surface in a region grad will also be a little bit darker, and so on and so forth. So it's sort of like we're reaching into like this large physical system. We're making a small non-physical artistic adjustment, but then because it's a physical system, we can kind of propagate the effects of that back out so that everything, even though we're making these like artistic adjustments that aren't necessarily physically accurate, we're still keeping everything kind of cohesive and tied together visually. So it still kind of looks, it looks plausible,
Right. That's amazing. So, and then one more thing I wanted to ask you about is like you keep up with the research and things that are happening in the industry. What do you see are the next big things coming? We've seen RTX card that provide for like faster rendering, almost at interactive rates, and then other things that are coming from Unity for promoting more real-time global illumination kind of things. What do you think are the next things that are coming?
Yeah, that's a great question. Kind of as Pete Shirley mentioned when he talked with you, the past kind of 5 years of ray tracing has seen this like huge explosion of new technology and new research and a lot of new incoming people from different adjacent fields, to the point where kind of almost all of like the rules about what we assumed was true about what was possible in ray tracing are now being rewritten on the fly underneath us. So it's a super exciting time. So for example, like you mentioned, the advent of RTX cards and hardware ray tracing has fundamentally changed a lot of the previous cost assumptions about like what the most expensive part of a ray tracer is computationally, which in turn is spawning completely new, completely different ways to think about things like light sampling or importance sampling. There was a paper at SIGGRAPH 2 years ago from Benedict Bitterly and a whole research group at NVIDIA that demonstrated that basically like, oh, well, we used to think of tracing shadow rays as extremely computationally expensive, but now that tracing shadow rays using RTX hardware is basically free, here's this entire class and this entire family of, real-time, temporally amortized, like direct light sampling algorithms that we can now use, which is really, really cool. And it kind of cracked open this entire new way of just thinking about stuff. I think another area that's definitely changing things a lot is machine learning. I mean, everybody in computer science is talking about machine learning these days because it's by far, the hot new topic, which is why Rajesh is this way. Rajesh is teaching you guys a course on that as well. And machine learning is kind of impacting every part of ray tracing. Machine learning driven denoising has unlocked a huge amount of just additional like render time improvement for us at Disney Animation. We use machine learning denoising extensively on all of our films. But aside from just denoising, machine learning is starting to be applied to a lot of other problems inside of ray tracing, like light sampling, like being able to learn light sampling distributions, being able to learn indirect illumination distributions so that we can import and sample indirect illumination, which is previously a thing that we could never do. And it kind of remains to be seen like what else it can be applied to, but at this point in time, it's sort of like if there's any problem that you can think of inside of ray tracing, there's probably a research team somewhere that's figuring out how to apply machine learning to it to improve it.
That's awesome. So, and then in closing, do you have any advice for people new to the field who want to get in, and then what kinds of things they should be learning or doing?
Sure. So first off, if you're watching Rajesh's course on ray tracing, you're already off to a good start if you're getting started. Going through the ray tracing in one weekend and then the next week and then the rest of your life book series is, I think it's a really fantastic place to start because it really, there's a lot of math inside of ray tracing, but it's always presented in a way that's like very complicated and it sounds super fancy. And at least for myself, it's a lot easier to understand that stuff once I actually see how it's concretely implemented in code. And I think, this course and the Pete Shirley book series is such a great place to start to do that. And the other thing I would suggest is just, if you have the opportunity to go to SIGGRAPH as a student, or if you have the opportunity to watch SIGGRAPH online, or if you're even able to just like catch the lecture recordings and stuff that are often posted to the ACM Digital Library or to YouTube afterwards. That stuff is always great to watch, even if you're starting off and you kind of are totally lost in all of the fancy terminology and stuff. Like something that I did in school was I was fortunate enough to be able to attend SIGGRAPH as a student, and I would go to all of these paper presentations about advanced topics that went way over my head, and I would listen anyway and try to glean what I could, and I would just keep a notebook with me and I'd write down every single thing that I didn't understand. Then afterwards, I would use that as kind of a starting point to go, reading on my own and do sort of like almost like a recursive deep dive through everything that I didn't know. Like, okay, here's a term I heard in a paper presentation. I don't know it. What does that mean? Read it. And then like, oh, there's all this other stuff I don't understand. And I would just keep going until I eventually started to build up like a better understanding of everything. So yeah.
Awesome. So again, Karl is being modest here. He also does a lot of artistic stuff, and 2 years in a row, I think he's placed very highly on the Pixar Renderman competition. And you want to describe a little bit? You have details on the blog, I know, but just to hear from you, like how you came to do that work and what was it like?
Sure. Yeah. So I've been a strong believer in kind of trying to. I'm a strong believer in like basically dogfooding your own tools, which basically means like if you are a engineer developing a tool for a user like an artist or something, the best way to kind of understand what the tool is missing and what the experience of actually using the tool is like is to just try to use it as your user actually would. And so for me, like a big part of learning how as an engineer I can better improve like how artists are using our render and improve like the tools that are available inside of our renderer and all that. A big part of me for that is just trying to use a renderer to actually go make pictures in the way that an artist would. So basically like play at being an artist for a little while to understand what it's like to be an artist. And then use the takeaways from that to improve what I do as a developer. So that's kind of how the whole Renderman thing started, or the Renderman Art Challenge thing started. At the time, so I even though I work on a proprietary renderer at Disney Animation, I like to keep an eye on what all of the other commercially available renderers out there are doing because I know a lot of the people on these teams and they're all super smart and they're all doing super interesting stuff. So I always try to make sure that I'm, every once in a while I'm playing with Renderman or V-Ray or Arnold or whatever, just so I know what's out there, and I can, see how that compares to what we're doing, and see, if there's anything from, those packages that we can learn to help improve what we're doing, or if there's anything that we're doing better or whatever. And so when the Renderman group started putting out these art challenges, I thought that was just a fun excuse for me to go play with Renderman and see what the latest and greatest was. And the fact that I did well in this contest was kind of a surprise to me. that wasn't the intention, but I guess that was a nice bonus. But yeah, I think along the way I learned a lot of super interesting stuff about what modern Renderman is like, and there's stuff in there that's really cool, and yeah.
Awesome. Again, thank you for taking the time to be with us, and I think we learned a lot today. So thank you again.
Yeah, thanks so much for having me, Rajesh.
No problem. All right, so that was Karl, and I think we heard from Karl. We're talking about what it is to work on a commercial renderer that can produce production quality images at high resolution with millions of objects and tracing billions of rays. So let's get back to our renderer, which is far more simpler because this is an introductory course. So last time we covered a simple ray sphere intersection. So the way we did that was essentially shooting rays from the eye towards the screen, through the screen pixel towards the object, which was in our case a sphere. So we will have all our objects as spheres so that it remains easy to program and it's fast enough in shader toy. So for the ray, we compute an equation that goes from the eye point and then goes into the scene, and we see if it hits the sphere. So that is simply taking the equation of the sphere and then equating it to the ray, and then trying to solve for the unknown, which is the hit point. And while solving that, we come across this quadratic equation, which we can solve using a discriminant, which is the square root of b squared minus 4ac. And there are two possible values of intersection, as you can see from this blue line. And we did that, and then we try to find the closest intersection point to the eye. So we'll ignore the second intersection point, and there may be cases where the ray doesn't hit the object at all. In that case, the discriminant is less than or equal to 0. And there may be cases where it just grazes barely, and there'll be only one solution at that point. So we use the smaller t, which is going to be our intersection, which is the closest point to the eye that is visible. So this is basically a basic visibility test of an object, if the ray hits the object or not. So continuing on from that, we also did a simple shading model where we said that if we look at the ray from the eye and it hits the object, we find the normal at the hit point. So normal for a sphere is really simple. All you got to do is, if you find the hit point here, you can take the line from the center of the sphere and project it outwards. So that's the normal. So everywhere the normal basically points outwards from the sphere. And so it's really easy for us to calculate the normal at any point on the sphere. So once we find that normal, we can also then find the angle that the ray has with the normal. And if you look at it, the more front-facing something is, the smaller the angle is. So this particular ray, R2, it is hitting almost in the center of the sphere here. And if you take the normal, which points this way, the angle between the ray and the normal is almost 0. So if you think of what you are viewing as a headlight, essentially, near your eye, then this part should be the brightest. And as you go away from it, things become darker in color. So that's the essential basic shading mechanism that we can use just based on the angle of the normal with the ray. So that's what we did. And the easy way to calculate the angle is just to normalize these two vectors, the ray vector and the normal vector, and take a dot product. And dot product of two vectors is proportional to the cosine of the angle, and the cosine, as you know, as it is tending to 0, the value becomes 1. So you would then use that to modulate the color. So if you get the value of 1 here and 0 over here, so there will be almost no contribution, and as you increase or you decrease the angle, you would have full lighting over here, and then slightly diffused all the way around. So that's the mechanism we use for shading, and this is diffuse shading. And what we can do, so the light doesn't have to be at the head. We don't have to have the light exactly at the head. We can move the light anywhere. So what we can then do is move the light somewhere else into our scene and use the same mechanism, basically. We take the normal at the hit point, and this time, instead of taking the angle from the viewpoint, we take the angle from the light itself. So in this particular case, you would see that this normal is almost parallel to the vector from the light. So this part is going to be the brightest. And as you go away from the light, the angle starts decreasing, and you'll get less and less light here. So this particular thing is called Lambert's cosine law. And these surfaces that kind of exhibit this property, they are called Lambertian surfaces or diffuse surfaces. So this particular shading scheme is independent of the viewing angles, which means that you look from anywhere, it doesn't change. All that matters is the light position and the angle it is making with the object, or the normal of the object. So the smaller the angle, the more the intensity, and as you move away from the light, you get less intensity, and you can use that cosine value to modulate the surface color, and that will give you a diffuse. So diffuse objects are things that are not emitting light, they're not reflecting light, they're kind of like a cotton cloth almost, or a diffuse paint. So you can use, there's specific set of objects that exhibit this property of being Lambertian or diffuse, and are view independent and only depend on the position of the light and the object itself. So let's try to program this and see how far we can get. So now I am sharing the shader toy, and you can find it in my profile. It's called Class 3 Shading Lights and Textures. So this is what we had last time. And as you can see, what we did here was we found the hit point, we found the normal, and we created a vector from the hit point to the center of the sphere, and another vector from hit point to the eye, and then took the dot product of those, and then used that angle to modulate the sphere color. And that's why we are getting this shading. So as you can see, this is for a light that is at the camera or at the eye, and that's why you see the center part is being illuminated the most, and as you go away from the center of the sphere, you get this shading effect that is proportional to the cosine angle. So let's take the headlight from the eye and move it somewhere else. So if we generalize this, what we can see is we, instead of taking hit point to the eye, we say hit point to the light. And here we can use, say we have a light object. So assume we have a lights object with a location, and then instead of taking the ray direction, we will make a vector and normalize it from the light location to the hit point, and that should give us the angle. And let's try to compile that. So what I did here was behind the scenes, I created this lights object. It's an array of just one light. And for checking the sanity, I put the light at the eye point or the cameras. But we can change the light direction now. We can put the light somewhere to the top left of the scene. So -1 in X direction and -4 a little bit back. The sphere is placed at -6, so the light is somewhere a little bit ahead of the center of the sphere, but on the top left side. So as you can see, the light has now shining from the top left, and you see the variation from the light's point of view. So that's pretty cool. So we're done very simple lighting for Lambertian surfaces, essentially. So our, whatever the viewpoint, the lighting doesn't change, and it looks pretty nice. And you can move the light if you want. Let's see if we can move the light a bit. So we can add a frame. Move it slowly, maybe frame over 100. So it will move from left to right. So f is an integer. Let's make that floating point. So what I did was make scene. I'm giving f as the frame, and we are going to change the x component of the light that will make it move from left to right slowly. So every 100th of a frame, it will move a little bit. So let's try that. So it's moving slowly. Maybe get a little bit faster here. So that's the effect we're getting. So that's pretty good, and it looks like what we would expect if the light moved from left to right. So let's leave it at the top left, and it should be fine. Okay, that's good. There's simple lighting, so now we're getting somewhere. So it looks a little bit more realistic, a little bit more proper. There'll be other kinds of lights we would implement, other kinds of materials, so they're not just diffuse and they vary with the viewing angle. So we'll do that in the next class when we look at materials in more detail and what they are composed of and how different kinds of materials behave with the lights.
At SIGGRAPH 2020, more than 10,000 individuals from 95 countries gathered virtually to experience over 350 hours of content presented by more than 1,600 contributors. What resulted was pure SIGGRAPH. Robotic advances use subtractive fabrication techniques to carve foam and similar materials like an artist. Modeling and predictive computation creates a more robust and accurate time-stepping of nonlinear elastodynamics. New investigation into damage simulation could change the landscape of video and game effects, as well as surgical training. Novel healthcare technologies point toward new ways to transform and enhance lives. Research will help users to create reprogrammable multicolor textures made from a single material. AI-driven technology pushes the capabilities of crowd simulation. Award-winning animation showcases the latest in computer graphics. Real-time and gaming technology advancements transform interactive storytelling techniques and explore new applications of the technology. Evocative digital artwork uses machine learning to create visceral experiences. Now is the time to share your research, your innovations, and your creative inspiration. SIGGRAPH is your community, and we hope you'll share your work with SIGGRAPH 2021.
All right. So I'm back. Sorry about that. My computer crashed and decided to install updates at the same time. So thank you for waiting, actually. So let's pick up where we left off. So we did simple shading, and now we have a simple light source that we can place anywhere for basic diffuse shading. So that was one thing. So let's talk a little bit about texturing now. So far we've been using simple color that we return for an object. We don't have to limit ourselves to that. So we can modulate the color of the object by any signal at all. So a common practice is to use a texture or an image that has some UV coordinates that we can map onto our objects. So that's called texture mapping. And an easy method is to take this flat image, what we would call a UV map or a texture, and then wrap it around a sphere that we have as our object. So this mapping causes discontinuities at the pole, because as you can see, all the top row items of this UV map, they are going to all converge to a single point. And same thing will happen at the other pole as well. And the rest of it gets kind of stretched out, and it becomes a little bit stretchy, but it's a good way to kind of take this texture and map it onto objects. So for things like cylinders, you can do a perfect UV mapping without distortion, but for sphere, you will get some distortion. And the way to do that is usually you would take a position on the object, dx, dy, and dz, and then convert that into u and v values, that range from 0 to 1. And you use that UV value to look up into the texture. And you look up into the texture for a color for the corresponding U and V, then you map it back to the object here. So let's try to do that. And so where can we do this? So anytime we are tracing the ray and we return the color of the object, instead of returning the color, we can right here process instead do the UV. So let's do a simpler projection and based on the normal, because we already have the normal now. So what I'm going to do here is type something for the U. So you need to find out a U and a V. Oh, my computer's locking up again. Let me close some of these so we don't. Okay. So that's our U. Be similar. Okay, so now we've found the U and V, and we can now try to modulate the sphere color. Oh, computer problems again. Okay, so what we did was we said change the sphere color, and this time get the texture from this I channel. That's another input, and what the texture command does in GLSL is it takes the U and the V, and it finds the corresponding pixel in the texture, and we're saying that we're going to take the texture from channel 0, and it will then map it to a color that will give us the sphere color. So if we run this, it's all black because there is no channel 0 texture. So if you click on this channel 0 at the bottom, you get this menu, which is pretty cool, and you can choose any of these textures. So an easy way would be to let's choose this texture. Okay, my GPU is fighting. There you go. So that's a texture mapped sphere. And you can choose any of these textures. And this is a good texture to see, because now you can see how the distortion is happening at the poles, where things are getting compressed into a single point, whereas around the great circle, things are kind of expanded. So you can, again, choose different kinds of textures. This one is nice. There's a bunch of textures in here. And this one is kind of cool because it takes the image and distorts it. And you don't have to limit yourself to static images. You can take moving images, and you can have a movie texture mapped onto that. So it's basically every frame, it's doing the same computation. It's trying to use those UV coordinates to get the texture pixel, and then use that pixel to modulate the color. So that's pretty cool. And you don't even have to limit yourself to that. You can actually modulate this by music. If this ever comes back. So as you can see, the color is being modulated by the music signal is converted into a texture with UVs, and then you, at each pixel, you get some kind of a signal that is being changed by the music. Okay, so because this takes up a lot of GPU power and my computer is choking, I will remove this texture. So, but you get the idea. So you can do texture mapping. So that is a great way. So now you got two properties of material, a texture map and a color. So you can use a mixture of both to figure out like how a material can be. So a material of an object can be composed of texture and other properties as well. So we'll use texture as one of the properties of the material. So ultimately what we will do is we will specify the texture as part of the object with its color and material. So that way you will have that as a property of the object itself. So in the next class, we will talk about other properties of materials, and we'll go more into detail about what the objects are. So, but you got the idea. The simple texture mapping, we can do that easily. Now we move on to the multiple objects part. So so far we've had only one sphere, and it's very easy to extend that to multiple spheres. So all we have to do is keep track of the nearest object and the intersections. So let's see how to do that. And let me go back to my profile. So here, what I did was just extend our array of objects to have more spheres. So I made more spheres in the shape of my favorite Disney character. And essentially, there are now 1, 2, 3, and 4 spheres placed at different locations. And what I'm doing now that is different is trying to find out which sphere I hit. And then keep track of that. So as you would see, that this is probably not enough. So I also need to track the T, which is the minimum. So what change we're going to do here is essentially make sure that the the intersection that we are getting. It's not just the first object, but it's also the minimum t. So we would create a variable here. We'll keep track of the closest intersection point here. So, and then in the intersection itself, we change this to the minimum t. So that way, all the objects that when we, one by one, we traverse each of the spheres, and you find the intersection for each sphere. And if this intersection is the closest one we have found so far, then just save it. And then you don't want to break here. You want to keep the loop going. So you're saving both the index of the sphere that is the closest so far, and also the intersection value that is the closest so far. So by looping through this, what you would end up outside of the loop here is the object that is the closest to us, and that is what you want. And then you'll use that to do the rest of the calculations. So if you run this now, so now you see that objects are properly positioned. And the order that you list them here should not matter. So that is one key thing where you are keeping track of not just which sphere you hit, but also which intersection point is the closest as well. So now you have converted the Mickey Mouse into a teddy bear of sorts. So there you go. I think it looks pretty nice. We're doing 2 samples per pixel, so it's nicely anti-aliased and also eating up my GPU, but that's okay. So there you go. So we have made like pretty rapid progress from simple intersection to doing some lighting, to doing some texturing, and then handling multiple objects as well. And what I asked as homework last time was to be able to create complicated scenes, if you could. And one way to do that is have other kinds of objects. So all you need is to figure out the algorithm for intersecting that object with a ray and find the hit point. And then you also need the normal at the intersection. So any kind of new object you want to introduce, you make sure you're able to do these 2 things. Most common object that people use in ray tracing is the triangle, because you can compose any kind of complicated object with a triangle. And one of the common algorithms is listed here in the link. If you feel adventurous, go ahead and try to implement that. If you don't want to do triangles, then you can try for implementing a quadric. A quadric would be very similar to a sphere, really, to do the intersection. And here's a neat little formulation. So a quadric is defined by this kind of equation. It's still quadratic equation, and sphere is just a special case of this, where W is 1 and J is the radius, and most of these other terms are 0. So it basically is ax squared plus ey squared plus hz squared. So you can create spheres with this. You can create ellipsoids, cylinders, taking on different values of these constants. And one neat thing about this kind of formulation is that you can express it as a matrix. So if you have a matrix like this, which you can see it's symmetrical around the diagonal. So C and B and D, E, F, they're all symmetrical about this diagonal. So it's a nice little matrix. But if you take that matrix and put it in between here in this equation, where you transpose X, multiply it by this matrix Q, and then again multiply it by X equals 0, this, if you calculate that, it would work out to be this exact equation. So now you have a matrix form. You can do the intersection of the matrix with the ray, and then you can find the normal by doing differentiation. So it's a little bit more involved, but you would get multiple kinds of objects, and you'll not be restricted to spheres. And the derivation would be very similar to the one we did for the spheres. And in the ray triangle case, it's a simple intersection, but then you would have to construct your objects out of triangles. So that way you can go back to any 3D package, make a 3D model, and export it out as triangles. And then you would read those triangles in, and then you would be able to use this. So this is what most commercial renderers would do, is use either subdivision surfaces and then break them down into triangles and do ray triangle intersections. So again, for anyone implementing these things, if you send it to me via Twitter, I'll put you in a rank, and then we'll award copies of ray tracing gems, courtesy of NVIDIA. And I will take a look at the homework examples that you submitted last time, and I will award out a book towards the beginning of the next class. And also want to have a competition where you can start creating your scenes, and people who create the most spectacular of the scenes, I'll also give them copies of this book, again, thanks to NVIDIA. So one example I tried to make, if you go back to my profile, there is, so what I should do is save this out so you'll have this available to you. I tried to make a little bit of a complex scene. And this is an animated scene. As you can see, the spheres are moving around slowly, and I tried to do this procedurally, because as things get complicated, you will need to use some kind of a procedural methods instead of manually placing all these spheres. So I have this big sphere, and attached to each of the 6 points on the opposite ends, I have another sphere, and then I recurse. So essentially, you have 37 spheres here with one level of recursion, and I'm just moving those spheres around just for fun. And you can actually stop it. So you can look at this. So this thing, if you do it multiple recursions, it would become what is known as a sphere flick. It's kind of a Mandelbrot-like set where you just have recursive things with the infinite surface area, really. So try this out, see if you get some inspiration from that. So GLSL doesn't support recursion, so I had to kind of use an iterative method to make this. And let's take a quick look at how I did that. So it's really straightforward, really. So I have the first sphere that I made, which is our standard one sphere at the center. That was the big one. And it's placed at -6 in the Z, and color is random. Then what I do is I create 6 spheres. So I have this function add 6 spheres that will add 6 spheres, and I do this to each of the spheres that are around it. So add 6 spheres, all it does is it's all relative to each other, so you can change any of these numbers and they will all kind of stick together. So this sphere takes this radius of the original parent sphere and divides it by 2.8, so they are smaller, and then positions them towards each of those points on the sphere. So, and then if you repeat that, the next set would be its radius divided by 2.8, so it's a still smaller sphere. And we can play with this, actually. So we can make them a little bit bigger. So let's try 1.8. So all the spheres should get a little bit larger, and then they would kind of appear there. And you can also figure out like where they should appear. So right now I'm placing them almost at the tangent of the sphere. You can place them a little bit more outward. Or inwards. So if you do that, they will all kind of shrink a little bit inside. But they're all relative to each other. So you can take this bigger sphere, for example, the first one that we made, and you can move that closer. And they should all kind of stick together. So because they're all relative to each other. And then finally, the way I did the movement was just use the frame to kind of rotate things around. So I have a function here, rotate scene 10 degrees, and then every few frames I rotate it a little bit. And this particular rotation thing is called the Rodriguez formula, and you can look it up on the web. It basically takes two vectors and rotates one about the other. And that's what I'm using to kind of rotate 4 of these. So if you look at that, the big ones are rotating, the rest of them are staying in place. So that's a good way to build procedurally things that are a little bit more complicated. And if you go one more level of recursion deeper, it just will probably totally choke, because 36 is already too many for it. So that was making complex scenes. And then we did the hands-on. And just to give you a note about complexity of ray tracing, and I know I'll be a little bit over. Let me just take one more minute to cover this, and then we can end. And in the meantime, if you have questions, please start typing them, and I'll answer them at the beginning of the next class for sure. So if you look at what we have taken so far, like we are going through each pixel. So our complexity depends on the width and height of the screen, and we're doing multiple samples per pixel, and we're going through each object for each ray. And we also did this optional texture lookup per object, and then we're using color lookup per object, or shading, which we are not doing much shading yet, just a little bit. So all this thing adds up to the complexity, and these basically multiply with each other. Because we are doing that for each sub-sample in the pixel. So anytime you increase any of these numbers, if you make the image larger, you're going to end up with a lot of computation if you're going to use more SPP, or if you have more objects. So then it becomes important to kind of start optimizing for this. Like, how do we handle bigger numbers for each of these, like W, H, SPP, and T? Like, what would you have to do to make that faster and finish faster? So we'll talk about some of those strategies. We won't be implementing them. They can get complicated, and then Share a Toy can't handle many objects anyway to begin with. So we will talk about them in principle and what it takes to implement those kinds of things. That's about it for today's class. And next class, we'll do materials and reflection. We'll talk to Brent Burley, who's the person behind the Disney BRDF, and lots of other things like PTEX and SEX for expression language. So, but go ahead and do the homework, extend the intersection to quadrics if you can, add triangle intersection if you can, and add objects, make interesting scenes and animations, and send them to me through Twitter or LinkedIn. And then I will award a prize next class for sure. Thank you again. Sorry about the whole computer crashing, but that's what life is.
At SIGGRAPH 2020, more than 10,000 individuals from 95 countries gathered virtually to experience over 350 hours of content presented by more than 1,600 contributors. What resulted was pure SIGGRAPH. Robotic advances use subtractive fabrication techniques to carve foam and similar materials like an artist. Modeling and predictive computation creates a more robust and accurate time-stepping of nonlinear elastodynamics. New investigation into damage simulation could change the landscape of video and game effects, as well as surgical training. Novel healthcare technologies point toward new ways to transform and enhance lives. Research will help users to create reprogrammable multicolor textures made from a single material. AI-driven technology pushes the capabilities of crowd simulation. Award-winning animation showcases the latest in computer graphics. Real-time and gaming technology advancements transform interactive storytelling techniques and explore new applications of the technology. Evocative digital artwork uses machine learning to create visceral experiences. Now is the time to share your research, your innovations, and your creative inspiration. SIGGRAPH is your community, and we hope you'll share your work with SIGGRAPH 2021.